Okay, so in this next video, we're going to move on from the algorithm we introduced in the previous video, the Gaussian algorithm, and we're going to talk about what happens once you get to row echelon form. We mentioned that there's a simpler version of row echelon form, the reduced row echelon form, right? So once you get down to a row echelon form, you might want to continue on. And one of the reasons you might want to continue is that there are many different row echelon forms, but there's only one reduced row echelon form. The reduced row echelon form is unique, and everyone can agree on the reduced row echelon form. So finding the reduced row echelon form amounts to kind of continuing on. So the Gaussian algorithm, we mentioned this last time, gives us these forward steps, right? We move from left to right and top to bottom, and we create our leading ones. Right, so this was what we did in the previous, we saw one example, we ended with an example last time, right? So moving from left to right in each column, we create a leading one, and we make sure there's zeros below that leading one. We move on to the next column, we keep repeating, right? This is the idea. Now, that gets you to row echelon form, but you want to keep going from row echelon form to the reduced row echelon form. You'd like to simplify further. So where do we go from here? Well, there are two ways that we can proceed to the solution from a row echelon form. One is using what's called back substitution. So we kind of look at that bottom row first. That bottom row says, again, let's label these columns X, Y, Z. Right? So the bottom row says that 1 times Z equals 5, right? So Z equals 5. So now we know what Z should be, so we look at the next row. The next row says 1Y minus 3Z equals minus 2. Okay. Well, that means that Y is minus 2 plus 3 times Z, which is 5. So Y has to be 13. The top row says 1x plus 2y minus z equals 4. Okay, and so x is 4 minus 2y plus z. So that's 4 minus 2 times 13 plus 5. Okay, which is going to give me minus 17, I believe. There we go. Okay, and so now I know what x, y, z are. So x is minus 17, y is 13, z is equal to 5. Notice one of the reasons why the leading ones are quite useful is that in each one of these equations, right, we can immediately solve for the first variable, that leading variable in each equation, the one corresponding to the leading one, right? All we do is throw the other stuff to the other side and we're done. Now, Gauss-Jordan elimination is a continuation of this algorithm using row operations, but now in the Gaussian algorithm we work from the top down. We get this staircase of leading ones. In Gauss-Jordan elimination, now we work backwards, and we go from the bottom right. We start at the bottom right, and we kind of go back up, right? So from the bottom right, we go back to the top left, right? We go in the opposite direction. But this time, instead of creating zeros below our leading ones, we create zeros above our leading ones. Okay. So we start now not on the leftmost column, but the rightmost column, and we say, okay, in that right, not the constants, but the rightmost variables column, right? The sort of the leading one that's the furthest to the right. We say, okay, how can I use that leading one to get rid of any non-zero things above it? Well, in this case, we see that we should do, if we do row 1 plus row 3, and make that my new row 1, I'll get rid of the minus 1. Then I can do row 2 plus 3 row 3, make that my new row 2, and that gets me to 1, 2. So minus 1 plus 1 gives me the 0 I'm looking for. 4 plus 5 gives me a 9. Then 0, 1. So minus 3 plus 3 gives me a 0. Minus 2 plus 3 times 5 minus 2 plus 15 gives me 13. 0, 0, 1, 5. Okay, and so now that leading one is the only non-zero entry in its column. The first leading one is always the only non-zero entry in its column. We've got one left to deal with. What do we have left? We've got this 2 here. We got to get rid of that 2, but we know how to get rid of the 2. We take row 1 and we subtract 2 row 2 and make that my new row 1, right? 2 subtract 2 is going to give me my 0 that I'm looking for. So I get 1, 0, 0. And so now I got to do 9 minus 2 times 13. So 9 minus 26 gives me minus 17. 0, 0, 1, 5. And now we're in reducer echelon form. Okay, and you can also see that from reducer echelon form you can immediately read off the answer, and it's the same as before, right? The first row says x is minus 17, second row says y equals 13, third row says z equals 5, and you're done. Okay, all right. Here's another example. We'll apply the Gauss-Jordan algorithm here. Now, one of the back substitution is fine. You can do back substitution. One of the places where we're continuing all the way to reducer echelon form is useful is when there are free variables. If there are parameters around, it's nice to continue all the way. We know that in this system, if there is a solution, we're going to have at least one free variable because we have more variables than equations. It's not going to be possible to completely determine all 4 variables. We're not going to be able to get a unique value here. So, start with the augmented matrix. 1, 2, 1 for the x1 variables, minus 2, minus 4, minus 2 for the x2 variables, minus 1, 1, 2, 3, 0, minus 3 for x4, 1, 5, 4 for my constants. Okay, so I've already got a leading 1 in the upper left-hand corner, so we leave that alone. We don't want to lose our leading 1. We've got it right where we want it, so we keep it there, and we use it to create zeros below. So we do row 2 minus 2 row 1. That's going to be my new row 2. Row 3 minus row 1, if I make that my new row 3, that's going to get rid of the 1. Okay, 1 minus 2 minus 1, 3, oops, got ahead of myself there, 3 bar 1. So 2 minus 2, 0, minus 4 plus 2, 0. 1 plus 2 gives me 3, 0, minus 6 gives me minus 6, 5, minus 2 gives me 3. Okay, now row 3 minus row 1, 1 minus 1, 0, minus 2 minus 2, 0, 2 subtract minus 1, 2 plus 1 gives me 3, minus 3 subtract 3 more, minus 6, and 4 minus 1, 3. Okay. So, now you notice, hey, look at this, guys. This row and this row, those are the same. So here's what I would do, right? I'm going to be a little bit lazy because I know what's going to happen. I know that that second row is going to cancel the third row. I know that that's going to be gone, right? So I'm gonna kind of say, well, one of the things I'm going to do, there's going to be a step, but I'm going to skip it. I'm going to do row 2 minus row 3 and make that my new row 3. But I'm not going to bother to write down that step because I know what that step's going to be. It's just going to create that row of zeros on the bottom. Sorry, row 3 minus row 2. mixed up my subscripts, row 3 minus row 2. The other thing I need is, well, I need in the row 2, I need that this 3, the first non-zero entry in that row, I need that to be a 1. I need a leading 1. How can I get a leading 1? I can divide by 3. So I'm going to 1/3 row 2, make that my new row 2. Okay, so I'm not touching row 1. And remember, I don't want to, right? Once I've got this column here with zeros below my leading 1, I forget about that first row and that first column, and I work with the smaller system that's left. And then you might say, hey, the first row or the first column in that smaller system, here's one of those places where that first column might end up being all zeros. That's a column of zeros, so I don't really worry about that. Really, I should be working just on this smaller system here, right? So I'm not going to do anything that affects, I'm not going to do anything using row 1, because anything using row 1 might get rid of these zeros I just worked hard to create. So I'm going to divide by 3 in row 2, 0, 0, 1, minus 2, 1, 0, 0, 0, 0, right? So those rows, that row of zeros at the bottom was created in this step that I didn't bother to write down. Okay, at this point I'm in row echelon form, right? I've got my leading 1s. My row of zeros is at the bottom. My non-zero rows begin with a 1, right? Below my leading 1s, I've got zeros. This guy is in row echelon form. It's not yet in reduced row echelon form because of that guy. Okay? So at this point, I've done the Gaussian algorithm. I've done the forward steps. I'm down to row echelon form. Now I kind of do this backward steps, and there's only 1. I got to get rid of that minus 1 to get down to reduce row echelon form. So I do my Gauss-Jordan steps. So I go, how do I get rid of that 1? Row 1 plus row 2 is going to be my new row 1. 1 minus 2, 0. 3 minus 2 gives me 1. 1 plus 1 gives me 2. 0, 0, 1, minus 2, 1, 0, 0, 0, 0, 0. Okay. So what I get here is I'm in reducer echelon form now. This is reducer echelon form. Let me jump up to the top. So the first equation says this. It says x1 minus 2x2 plus, notice there's no x3 in there, but there's an x4 equals 2. The next one says x3 minus 2x4 equals 1. Okay? So notice that first equation I can quickly solve for x1 in terms of x2 and x4. The second equation I can quickly solve for x3 in terms of x4. I don't say anything about x2 and x4. Those guys are actually my free variables here. So x2, x4 are free. Okay? You can leave them as x2 and x4 if you want, or you might, if you like. I prefer to do this. I prefer to say let's assign them to parameters. So x2 will be s, x4 will be t, and so then this is my solution, right? So I get the following solution. I get x1 is going to be equal to 2 plus 2s minus t. x2 is simply s. x3 is 1 plus 2t. x4 is equal to t, and s and t here can be any real values that they want, right? So I've solved my system, right? This is the best I can do for solving this system. I give values for x1, 2, 3, and 4. They depend on 2 parameters, but I can't do anything about that, right? I have infinitely many. This is a case where I have an infinite number of solutions, okay? Because, I started with more variables than equations, and that row of zeros tells me that actually my third equation was redundant anyway. So really I only had 2 equations with 4 variables. And With two equations, I can only really eliminate two of those variables, so I'm left with two that are free to take on whatever values they want. And so that's my system, my solution in this case. Okay, one more example. What do we get here? So we follow the same procedure. Step 1, augmented matrix. 1, 0, 10, 5 for the first equation, 3, 1, minus 4, minus 1 for the second equation, 4, 1, 6, 1 for the third equation. Okay, again, things were handed to us in a convenient fashion. There's already a leading 1 where we want it, so we've got to use that leading 1 to create zeros. So we're going to do row 2 minus 3 row 1 and make that my new row 2. I'm going to do row 3 minus 4 row 1 and make that my new row 3. Row 1 stays the same. 0, 1. Nice thing about that 0 in that second column means I don't have to worry about what goes on there. Minus 4 subtract, minus 4 minus 30. So minus 34. Okay, we can handle that. Minus 1 subtract 15. Minus 16. Alright, then 0, 1. 6 subtract 40. Uh-oh, that's another minus 34. And 4 times 5, that's 20. So 1 minus 20. I get minus 19. Okay. Let's double check. Did I make any mistakes? I don't think I made any mistakes. Minus 1, yep, I think we're good. So what does this mean? Well, let me do one more row operation. Row 3 minus row 2 is going to become my new row 3. 1, 0, 10, 5, 0, 1, minus 34, minus 16, 0, 0, 0, and minus 3. Okay, so I stop at this point and I say, is there, this is not I mean, I guess it's technically not in row echelon form because this guy is the first non-zero entry in the third row, right? But do I care? Do I continue reducing from here? No, I don't do anything more because what does that third row tell me? This third row says that 0 equals minus 3. Well, that's not true. So what can we conclude in this case? That third row is a contradiction, and that means that there is no solution to this system. By the way, this is one that you might find interesting to go ahead and maybe ask a computer to plot it for you, see what happens. Right? Each of these equations gives you the equation of a plane. Right? The fact that there's no solution, there's a number of ways in which three planes can intersect in ways that don't give you a solution. Right? So there's no point that's common to all three planes. Probably what you're looking at here is something where one of the planes kind of goes like this, and another plane goes like that, and another one goes like that. So you kind of have some sort of, intersection like this going on. It's kind of hard to sketch this thing out, right? But you have this sort of picture here. So, those planes intersect along, so there are points that these two planes have in common. There are points that these two have in common, but that you get this kind of they form this sort of triangle, this triangular tunnel between the planes, right? And so there are points that are common to any two of the three planes, but there's nothing that's common to all three, and so there's no way to solve the system in this case. Okay, one last example, and then we'll call it a day. How do we solve this? Let's fix that. This should be an equal sign, of course. That's an equal sign, not a plus sign. Missed the shift key there. Let's proceed to solve. 3, 2, 4, 4, 3, 3, 1, 0, minus 1, 1, 0, 2. Okay. What do we want to do here? So this time you might notice There is no 1 in the first column, right? There's lots of non-zero entries in the first column, but none of them are equal to 1. So now I choose. Do I want to divide, let's say divide by 3 and create fractions? If I'm a computer, I probably do. As a human, I think what I'm going to do here is I'm going to do this. I'm going to do row 1 minus row 2 and make that my new row 1, right? Because 3 minus 2 gives me a 1. 4 minus 3, 1. 1 minus 0, 1, 1. Okay. That's a little better. Alright, now I've got my leading 1, and I can use it to make some zeros. So I'm going to do row 2 minus 2 row 1. That's going to be my new row 2. Row 3 minus 4 row 1. That's going to be my new row 3. 1, 1, 1, 1. 0, 1. So 3 minus 2. 2 minus 2 gives me 0. 3 minus 2 gives me 1, 0 minus 2 gives me minus 2, 0 minus 2 gives me minus 2, 0. 3 minus 4, minus 1, minus 1 minus 4, minus 5, 2 minus 4, minus 2. Alright. You guys that are playing along at home, make sure my arithmetic is correct. I'm trying not to take up too much time on these videos, so there's always a chance that I mess up. Okay. Now I've got 1, 2 leading 1s. Again, be careful at this stage. Don't do anything with this. This guy's out of the picture. We're working here on this smaller system. And we see what do I want to do. I want to use that leading 1 to get rid of the minus 1 that's below it. So I should do row 3, plus row 2. Make that my new row 3. 1, 1, 1, 1, 0, 1, minus 2, minus 2, 0, 0. So minus 5, minus 2, minus 7, minus 2, minus 2, minus 4. Okay, at this stage, you got no choice. You got to bring in the fractions, right? They show up sometimes, and there's not much you can do about it. The next thing I got to do is minus 1 over 7, row 3. That's going to be my new row 3. So we recopy the first two rows. 0, 0, 1, and 4 over 7. Okay. This is in row echelon form, right? I've got my leading 1s, leading 1, leading 1, leading 1. I can choose from here. I'm gonna give you guys the exercise. Of finishing. And you've got two choices for finishing this guy off. You can finish off using back substitution, right? We know that z is 4 over 7 now. Work your way back. Do you want to do back substitution, or do you want to continue the row operations all the way down to a reduced row echelon form? It's up to you. You might want to try it both ways, see which one you like better, and that might inform your process going forward as to which method you want to use.